Well, we're back. We've got this nice result. Remember, this is the impulse response function for an ideal low-pass filter, and we want to find h of n so that we can now apply it to data. So we've worked our way backwards from an ideal frequency response to now we've got a function that we can actually apply to data. Let's sketch this thing. This is a good skill for you to have. We want to sketch h of n. And let's go ahead and assume a value for omega c so we have something to sketch. And I'm just going to pick out something. Omega c is pi over 5. Okay, and so let's sketch it. One thing we know about sinc functions is, I'll just sketch a real small one here, is that these zero crossings are always of big importance. And the way the sinc function is defined is these zero functions occur when the argument is equal to 1. So this happens when n omega c over pi equals 1. So let's solve for the zero crossing. So we've got n omega c over pi equals 1, and that means that n is equal to pi over omega c. Well, of course, in our case, and there's a plus or minus here, by the way, since it can be here or here, and that just, when we plug in pi is or omega c is pi over 5, we get n is equal to plus or minus 5. Okay, so now we're ready to draw, to kind of sketch out what this sinc function looks like. And see if I can draw a couple axes, relatively straight lines. Let me sketch the envelope. I'll pick a little bit different kind of a font. I'll see if I can sketch in the envelope of a 3, 4, 5, and go the other way. It's kind of a funny pen I'm using, but what I tried to do is put the, I didn't quite get it. There's 1, 2, 3, 4, 5. So there's the zero crossing right there. I kind of missed it a little bit, but I hope you get the idea. So that's the envelope. And then within that, we've got the discrete time sequence h of n. There's one, and these are delta functions, right? So we'll draw them with little balls on the top. And then this one occurs right there. And they keep going like this. Like that, both sides, both directions. Like that. What else? The sinc function we know has a value of 1 when the argument is 0, but it's also multiplied by a omega c over pi. So and omega c is pi over 5, so it's a over 5 is the value right there. All right, so this is a function of n. So questions. Is this a causal system? Remember, it's a low-pass filter, so we're calling it a system, has an input and an output. Is it causal? So if I hit it with an impulse at n equals 0, are we going to have any troubles with the output occurring before the input? And clearly, since this is h of n, clearly we do have a lot of output of the system before an input at n equals 0. So the answer is no, it's not a causal system. So the ideal low-pass filter is not causal. Well, we should have suspected this, because whenever you're asked to do anything ideal, you're going to get a result that's not realizable. What else? Another question. Just since we're just learning this stuff, is h of n periodic? A lot of this stuff just seems to be periodic. What about h of n? Well, we see a sinc function. You know, a sinc function just wiggles its way and decays forever, never quite decays to zero, so there's no way it can be periodic. So the answer to that is no. All right, well, that's enough of that example, and it's a very important example, ideal low-pass filter, and we'll worry about ways to get realizable low-pass filters later on. The next example I wanted to work with, number 2, is what is the discrete time Fourier transform of a single rectangular pulse? Okay, we're very interested in the rectangular shape because it shows up here as a low-pass filter in the frequency domain. In the time domain, it shows up as a way to transfer information if we're using digital communications. Lots of different uses for rectangular pulses. So we're very interested in finding its discrete time Fourier transform. All right, here, let me just draw what I'm talking about. So here we're going to call this x of n. Now we're in the time domain, and it's going to be rectangular in the time domain. The one we just got done with was rectangular in the frequency domain. So here's my rectangular pulse train. A bunch of Kronecker delta functions that switch on at 0. And for negative time, there's 0. But for positive time, there are a bunch of delta functions. And we're going to assume there are L of them. All right, so I'll sort of highlight this with red. There are L delta functions, and that means that the last one is at L minus 1, and we get 0 from thereafter. Okay, that's our function. And the pulse length is L. All right, so let's find the discrete time Fourier transform. It's actually pretty easy, except we'll carry it a little further than you might think we'd want to. But let's go find it. As you remember, the discrete time Fourier transform is the sum of x of n, and the sum goes from minus infinity to infinity, e to the minus j omega n. So that's a simple thing, and it's especially simple here. We've got the sum n equals 0 to L minus 1 of, I'm just going to say these are unit heights, e to the minus j omega n. Now, what we're going to do is use this thing we've used over and over again, this identity, that we can show that if we have a sum from 0 up to some n minus 1 of some constant raised to the n power, we can write this in a closed form solution as 1 minus a to the n over 1 minus a. So this thing, and there's different variations on it, but we use this a lot. Okay, well, clearly, if a is e to the minus j omega, we can just invoke this thing directly, and we get 1 minus e to the minus j omega L over 1 minus e to the minus j omega. Okay, so that's the Fourier transform. Now, however, we're not done yet. We can get this into even a better, more easily understood form, and so that's going to be a skill that I'll want you to know. We want to get this into a form that looks like this. it's going to be some e to the j theta of n times a, excuse me, there's my eraser. There it is. That's omega. Times a of omega. So we're going to have a purely real part and another part that contains most of, but not all, of the phase information. Okay, so it's very useful to get it into a form that looks like this. Okay, and this is called a continuous phase representation. All right, so that we'll talk about on the next video.